Have we all seen one of these before? I bet we have. This and this specific one right here, I bet you have. If you bought any cheap RGB stuff from China, like on AliExpress, on Temu, on Alibaba, it's probably come with one of these remotes. You can see it's an infrared remote, so we've got the little IR LED emitter out there. And essentially this is going to be sending out light pulses that are invisible to the human eye in order to wirelessly communicate with whatever LED device we're going to be connecting with. It's got all of these little presets here. You can see it's not 16.8 million colors. It's just got RGB and then a couple of, standard presets from that, but that's okay. Essentially, this is great if you love pointing and clicking at things. Like, oh, isn't this great? I love pressing these buttons. They're so tactile, this is like a Cherry MX Switch right here. It's great if you love doing that, but I don't. I want these things to update automatically, and I already have existing in my smart home infrastructure like Philips Hue lights that are connected over Zigbee. And so it would be great if I didn't have to point and click to change these cheap ones as well, if they just all change together. So that's what we're going to be doing. Basically, what I want is to be able to get a Raspberry Pi to pretend to be this remote and send off the signals as if it was this remote. And if it's a Raspberry Pi, of course, then we can say, let's do this over the network. Let's send this a network packet, and then it'll change the lights for me. And that's going to be fantastic. That's what we're going to be doing today. We're going to be looking how you can capture the IR signals from this. And then we're going to look at LIRC, which I think stands for Linux Infrared Control or something like that. It's a program you can get on your Raspberry Pi, which is essentially going to let you act like one of these remotes, and that's what we're going to be doing. You can do this for not just this is going to be the example, like you could use it for an aircon remote, you can use it for a TV remote. There's so many infrared remotes that you could use, and so many different protocols, and it's really interesting stuff, but we're just going to focus on this one as the example. Of course, you can make it whatever you want. Let's get into it. Of course, over here, this is my Raspberry Pi. I'm using a Model 4B. This already has the GPIO pin headers soldered. If you're using a 0, you might have to solder these yourself because we do need to use GPIO for this project. I've got these two little boards here. Now, these you don't actually have to buy as boards. This is the receiver module and the transmitter module. So these are actually really, really simple circuits. This one is literally just this thing here and this resistor. You could put this on a breadboard very easily. You could put it on your own custom design very, very easily. This one makes a bit more sense to buy as a module just because it's got this BJT over here to give this thing a bit more juice, and it's got these resistors around. So I was just like, you know what? I want to make my life really easy. This thing costs like $2. I could either buy all these components individually, do them all up on a breadboard, or I could just buy this and make my life really easy. So that's what I decided to do. But if you want to do your own custom design, these circuits are really easy. You don't have to buy a module like this. Basically, what's going to be happening is this receiver, we're going to be pointing this thing at it, and we're going to boop, 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 and just capture all of the codes, record them, and then we know what we need to play back using this transmitter. Now, to capture these, I'm actually going to be using this Arduino. The reason I'm going to be doing that is because the capturing of the scan codes, they're called, is grunt work. We don't actually like doing that. There's a very, very well documented library that's really easy to use. It's like a 50 line of code copy and paste from the internet that you can put on this Arduino to get it to scan in all of these codes. And I can't be bothered to do this grunt work, like do research into it. You just want to get this part done. So I'm going to be using this Arduino. And then of course the interesting stuff is playing this back over the network. So of course we need to do that on the Raspberry Pi. So that's what we're going to do. We're going to connect this receiver to the Arduino. We're going to collect all of these little codes. We're going to do up a little library and do up a little program that runs on this and listens over the network. And then it's going to be fantastic. I've gone and connected up this little module according to the pinout. So the black line is of course ground, the red line is 5 volts, and the green line is data. So over here we've got the black line being ground, the blue line being 5 volts, and the yellow line being data. You can see over here on my Arduino, I've connected the data line to pin number 2. I've connected the blue line, of course, to 5 volts, and the black line, of course, to ground. That's the hardware setup for this receiver. Okay guys, important setup you need to do on your Raspberry Pi SD card. Go ahead and plug it in, and you'll have a boot partition. So what we want to do on this boot partition is, so we've got all these overlays here, which basically enable or disable various functionality for the Raspberry Pi at a low level. What we're looking for is this config.txt right here. If you go ahead and open that up, you'll notice that down at the bottom here, I've added DT overlay equals GPIO IRTX. Why do you think we need that one, huh? We're going to be connecting our IR little transmitter thing to a GPIO pin. Specifically, I've used GPIO pin 14. You can use a different one, but I'll show a Raspberry Pi pinout on screen. What we need for our module is 5V ground and GPIO, and GPIO pin 14 is in the perfect spot for that. So go ahead and add this line in. I'll add it in the description in like a paste bin or something, but that's pretty much all you have to do. And then you can exit out of that. I've of course already made the change. And then eject your SD card and put it back in the Raspberry Pi. Now that you've got it all wired up, connect to your Raspberry Pi. I'll just SSH into mine, make this a bit bigger for you. The first thing we're going to want to do is install LIRCD. So if I just go ahead and do an apt list installed, I'll show you the packages that I have. So I have LIRC, liblirc0, and liblirc client 0. Just install this one first. It probably pulls these ones in as a dependency, but I can't remember at this point. So maybe get all of them if it doesn't pull it in. Once you've got it installed, there is a config file that we have to change. So if you just do a vim on lircoptions.conf, actually I'll list out this entire directory for you to start off with. So it's etc lirc. You can see that we've got a couple of options here. So in particular, we want to edit this lircoptions.conf. So if I just do a vim on that, the driver is what we have to change. So it'll be something else by default. By default, that's funny because we're changing it to default. So make sure you change this driver line here to say default. Otherwise you'll get like a unable to transmit issue or something like that. So change this one to default. And once you've done that, I'm fairly sure there's a little daemon that we have to check. So let me just check that. Yeah, so you're going to want to make sure that the LIRCD is enabled. So you can do that with this command. And if you do this command, it'll start it at startup, and the -- now will start it immediately. So once you've made sure that that's working, that's great. This is the code we're copying and pasting from the internet. Credits to Ken Sheriff at arcfn.com. This is 37 lines of code, and all this is going to be doing is starting up our IR receiver and just decoding whatever it gets and printing that to the terminal, which is exactly what we want. I looked up doing this on LIRC on the Raspberry Pi on Linux. This is just going to be way more easier to get through the grunt work, so it's really this simple. So now I'm going to go and connect to our Arduino. And if I grab my remote and I just pointed at it and I press the red button, you can see this is what's coming up. So this is what happens when I press the red button. As you can see, the protocol I mentioned before briefly, there were different types of IR protocols. It's the NEC protocol, and this is the code for the red action. And we can verify this if I press the green button a couple times. You can see that this one is changing. This FFFFFFF basically just means repeat. I'm not exactly sure why it has the repeat that happens after everything, but this is just how this one communicates. So what we know is that if we want to tell the thing to turn red, we have to send F720DF on the NEC protocol and then immediately send a repeat afterwards. And that should emulate exactly what this thing is doing. So essentially what we can do is go and map this out. And the way that I like to do this is I'm just going to go through one by one. If you were using a different kind of remote, you would of course, press the appropriate buttons for you, but we can do things like, this is what brightness up, brightness down. We can do off, and oh, that's interesting. If I hold down the button, you can see there that it does a repeat. So there you go. That's interesting behavior that we might want to know later. The white is this. You can just go through the colors and spot the differences, and I'll show you what I've done up. This is the result of the grunt work. I've come up with a C library that you can use to control this little thing. I've done hash define sound here. Now this was me literally just going through the entire remote and just seeing what all the codes are and writing them out. I found that every packet always started with OXF7 and then it was followed by a command. So for instance, if I wanted to turn the cube on, I would have to say OXF7C03F and then it would turn on. So that's essentially what I've gone and done. You do these hash defines, or you don't have to do it in a C library. Like you could do it in a Python dictionary, a JSON file. You could do it in a Golang map. Anything that sort of just like maps, this is what the command is, this is what the code that I need to do is. And I didn't even end up using these hash defines. What I ended up doing is more like a map, right? So I'm using this array and these enums as essentially a map. So if my code wants to use this cube IR red, it'll hit this array and it'll figure out what the code is. And the reason I did that is because of this. Now, this, essentially the problem is, guys, I have Philips Hue light bulbs, which have a much wider color range than this. So when my lights all change in sync with each other, the problem is, how do I get such a limited color space to give the best possible option? Like if I'm selecting on my Philips Hue lights something in between these that this cube doesn't support, I want it to choose the best possible option from the colors that it has available to it. The way we can do that is with something called Euclidean distance. Now, I won't get too mathy, don't worry, but essentially the way that you do that, you essentially compute the square root of the powers of the difference between all of the numbers. And it looks a bit weird in code form. I'll put the actual proper math formula up on screen. It's pretty simple. I've mapped the closest RGB values. So if I get, I don't know, if I get my color picker, I can show you. So for instance, Cube IR Red 2, the closest RGB match for that is 240, 115, and 0. So it's this kind of orange color. That is the closest possible map. Now, if I choose on my Philips Hue lights that, for instance, it'll likely just go ahead and map, oh, okay, this is this RGB value. The closest match is this one. And that's what I wanted, right? So when I choose something on my Philips Hue that's in between these things that it doesn't support, it'll map it to the best possible option. And that's what this array is for, and that's what this Euclidean distance formula is for. You have this cube command buffer, this library, this is how this works, which is a packet length of 3. Now, if I want to set a command, you can see I've got this thing here. So cube set full command, pass it a UN16, because remember, this is a UN16. And what it'll do is it'll put the packet start in there, and then it'll shift into place. Now, why have I done it like this? The reason is, I want this library to be able to support what's called an arbitrary transport. So it's all well and good if I can hard code this thing, for example, you know, in this Arduino thing, oh wow, I can get it to do irreceive.send. That's great. I actually want it to be more flexible than that. So what my library actually supports is a custom transmitter function. I have a function pointer. CubeRFTX is actually the thing that is actually going to be transmitting this to the receiver module. This is a function pointer, and the reason it's a function pointer is so that the user can overwrite it. So here you can see I've got cube register TX, and you pass it in a function pointer for the transmitter. Now, this could be an I2C transmit byte, it could be an SPI transmit byte, it could be just a digital bit bash transmit byte, it could be a network transmission byte. See? Now we're thinking. So instead of being just like hard-coded to say, okay, IR send on the Arduino, you can make it more flexible and you can just pass in a function pointer, and that was the goal with that. It'll fill up this buffer, and then the cube TX buffer will just use the function pointer that you've defined here to transmit it. LIRCD is set up and configured. There's one more thing that we need to talk about with regards to LIRC, and this is kind of why I decided to make a video, because I don't feel like this is particularly well documented in many other places on the internet, at least in video form or in tutorial form, and that's the concept of an LIRC config. I don't know if config file is the right word because it's not for the daemon, it's more like a profile. So if I show you this, let's see LIRC and then .conf.d, I think is the directory. Am I getting that right? Yeah, lircd.conf.d. So you can see here that there is a config directory. And if I go ahead and vim the default one for you, you can see here that it's got this sort of, it's like a remote profile almost. So you've got all of these codes here that are mapped to the codes that we were uncovering before. And there's some extra information here, like the name, the number of bits, all of this pre-data, stuff like that. I'll show you the one that I did up for this particular remote. It's this one here. Now, this information here, low-key, like I found it by Googling around on the internet for like NEC profiles. As it turns out, and you might find this out as well, this remote actually already has a profile somewhere on the internet. And someone had already gone and done the reverse engineering for this and done the scan. And this is actually a fairly common remote, as you probably know. You've probably seen this one before. And so there was already a profile for this. Now, as you can see, we've done the Scancodes, which is stuff that I did myself, of course. But this pre-data stuff, like, just have a play around, see if you can find it. Like, look up what IR remote said your protocol was and see if you can find ones that are similar that you can use here. As you can see, this is why I decided to use the Arduino for, like, you know, just capturing it, because LIRC is a bit more complex. It's like more flexible, but it's more complex, right? And so essentially what this is going to do is whenever LIRC gets this, it'll send this, and the pre-data, of course, is OXF7, like I showed you before. So this is the config file. Now that we've done up the config file, if you remember before when we were mapping all of this out, we can actually now just get up and go and immediately start sending IR commands. So I've said F7 and I'm doing red, which is 20df, as you remember us mapping out before. So if I hit this and I hit the send button, the cube, believe it or not, just turned red, and I'll give you a proper demonstration of that in just a minute. But now, essentially, the upshot of this is that we are getting up and going, we are able to send all of the IR commands from our remote, and now we can wire this up to do it over the internet, because it's from our Raspberry Pi, and that's connected to Wi-Fi. Essentially, the program that we're going to be writing is going to be sitting on a network, and it's going to be listening for commands. And what's going to happen is essentially it's going to run a sub-process. If you guys are familiar with, like, in C it's fork exec, in Python it's sub-processes, in Golang it's like commands, exec commands. But essentially it's just going to run this little command and substitute this with whatever we tell it over the network. Alright guys, to demo this I have two incredibly simple programs. Over here on the right, this is what's going to be running on our Raspberry Pi. This is a very, very simple, it's a 38-line socket server. Literally all it does is spins up a socket server and it's going to listen for a 6-byte payload. What is that 6-byte payload? Well, the 6-byte payload is these codes over here. So essentially what this is going to be looking for is F7 and then the code. And it will basically, all it does is it gets that code from the socket. It decodes that as ASCII because we'll be sending it as ASCII. And then it puts that into the exec command and it executes that. So if you remember, we were doing the IR send command. Literally all this program does is listens on the network and then IR sends whatever it gets. Now look, this is a really bad practice. Do not use this code in production, because what this does is it will run in a bash command exactly this without any checks to make sure it's in the correct range. This is purely for demonstration purposes, okay? If you're serving a networked application, you want to check to make sure that it's a valid payload. So just be aware of that. Like, someone could send you a payload that's not what you expect, and maybe you're executing some random bash command that you don't know what it is. Anyway, on the left over here is the client. So this is basically the thing that's going to use this libcube that I've got over here. And specifically what it's going to be doing, it's going to do regular standard socket stuff. This is a 67-line bit of code, obviously not including the big library. But the point of this is to show you that this library that we wrote to control the IR, we can then hook that into a networked application and then get it to talk to this socket server over here. That's the point. So if you have a look at what we're doing, we do cube power on, cube set raw. Cube set raw is just going to be like, you know, set the, what do I say that? It's literally just like set the thing to be the correct color. Because I've got two color things here, right? I've got set color R, G, and B, which does the whole Euclidean distance thing. And then I've got cube set raw, which you can just specify one of these. And I'm just going to do hard coding for demonstration purposes, right? And then after this, I'll show you the full setup of what it's like interacting with my home server and my home automation stuff. So we power on, we set to red, we sleep to, we set to green, we sleep to, we set to blue, we sleep to, and then we turn off. This is dead simple, guys. So that's what we've got here. We've got a 68-line client, a 39-line server, and this is going to be able to send IR commands over the network. So let's get to the demonstration. Okay, guys, here we are. So on the left over here, I'm on Slateport, and we're going to run our socket server that I showed you. And over here on the right, we've got our client program. I'm on Sunyshore on my desk, and this is the client program. So if I hit enter, you'll notice it turn the cube on, turn it green, turn it blue, and then it'll turn itself off. And there you go, we can run that again. And this is all happening over the network on our socket server. You can see there it's receiving it, it's transmitting it over IR, and that's our networked connections. Something important I just want to note, by the way, is that the argument to IR send, this F7 command, this isn't actually the raw hex that it's going to be sending as the code. The raw hex that it's sending as the code was actually what we went ahead and defined in this config file. So as you can see here, you know, F7D02F or whatever is going to map to this exact hex code. So this is ASCII. This is the argument that you're going to be passing to the IRSend command, and that's going to correspond to this. The reason why I made them the same, like you could very easily have this be like, I don't know, like red 0, and it would work exactly the same. The reason why I've done that is because in the libcube thing that I had, let me just bring that up. TX command here, remember I said you could specify a custom one? I just snprintf the command to ASCII and then send that over the buffer. So that actually is ASCII, and then this is going to be ASCII in here. This isn't the raw hex. This is getting snprintf to ASCII. And then that's going to come here, and he knows, okay, if I get this in ASCII, I'll send this raw hex value. And so that's how that works.